Good afternoon, everyone. On this course, and the today's topic is the overview of global navigation satellite systems, which is a satellite-based navigation system. So, primarily, what we get through the satellite navigation is primarily the latitude, longitude, and height. So, basically, we are getting the coordinates and that we have to use for our application. So with perspective of remote sensing applications, with which I understand you must be acquainted now with the previous few lectures, that primarily GPS data we are using for the purpose of georeferencing of the remote sensing data sets in case of two-dimensional analysis, as well as photogrammetric data sets in case of the three-dimensional analysis. Now, this global navigation satellite system is actually part of our age-old problem, which is the origin and destination problem. Okay, so if we go back into the history, we have been using the different type of landmarks on the stones, trees, and monuments. So we are going thousands of years back in a very crude way, and thereafter the celestial navigation also developed, which was good for the latitude computation but was poor for longitude, because for the calculation of longitude clock was required, and thus we started getting good longitude values after 17th and 18th century only, when good clocks were invented. Thereafter many navigation systems or surveying equipments has been developed, such as the magnetic compass, gyroscopes, then radio direction finding systems got developed, radar and inertial navigation system also got developed. Thereafter, some major ground-based, tower-based systems were developed, such as the LORAN A, LORAN B, LORAN C during the Cold War era. So the US developed the LORAN C system, whereas the Russians developed the Chayka system. So these were ground-based systems meeting the requirements of the area of interest as per the Cold War era. So they were primarily focused on some land area and the Atlantic and the Pacific region. Now this LORAN C has been providing the commercial services to the shipping industry also. But the point which we want to make here is that this LORAN A, B, C and Chayka systems, these has been ground-based and tower-based systems, similar to the ones which we use today for mobile phones. However, they are very tall towers and definitely different in construction also. Okay, but these are tower-based systems. Thereafter, the Omega and Alpha systems were got developed, where the Omega system was providing global navigation system based on terrestrial tower-based network. Okay, so US, with the help of the friendly countries, they developed Omega, and at the same time similar system Alpha was also developed by the Russians for the global navigation requirements. Okay, so thereafter, when the Sputnik was launched in the early phase of development of the satellites, then the problem which was faced was that how to track the satellite. Where is it? Is it in the orbit, or is it in the desired orbit, or it required maneuvering because it is going out of path. So all that has been used with the help of the Doppler effect, Doppler shift method, and the location of the satellite in the orbit has been treated as the unknown, whereas the on ground we have stations which have known positions. Okay, so that is how we started getting position of objects in space with the help of the Doppler shift. Now, when this development of Sputnik was happening, so in the JPL laboratory, Frank McElroy was one of the scientists. So he gave an idea whether we can invert the problem. So what was the problem? So when Sputnik was launched, the problem was that we have coordinates known on the ground, but we do not have the location of the coordinate of the satellite in the space. Now, inversion of the problem means that the coordinates of the satellites are known in the space, but the receiver coordinates on the ground are not known. Okay, so that is how this known and unknown become important. So in one case, the known is on the ground and the unknown is in the space when we are tracking the Sputnik, whereas we tried now an opposite approach where the satellite coordinates are known in their orbit and we want to get a position on the ground. And this lead to the development of GPS. In the initial phase, a smaller system called Transit, it was developed. It was for the developed basically for the Navy, and it was again a regional system and not a global system. It was also meeting the requirement of specific areas as per the requirement of those days. But it was a regional system, so that is important to understand here. Once that technology has become perfect, then the GPS also came into being in 1995, basically with the final operational capability, with the declaration of initial operational capability in 1993. Okay, so primarily what we are covering in this lecture is a two-part, we can say. One is the computation of the coordinates and another is the navigation. So in the case of navigation, we may consider it as an origin destination problem, which may have different kind of solutions. It can be a point-to-point solution, or it can be the shortest path solution, as you do on the Google Earth nowadays. When you go from one city to another city, you choose the path using some web-based platform. So these two things are there. So GPS ultimately is actually a surveying device per se, in continuation to the magnetic compass, theodolite, tachymeter, EDMs, total stations, and thereafter GPS came. Okay, so let us not forget that. So primarily it meets the requirement of surveying and can be called a surveying equipment. However, since it is much digital in the form, it is integrated with the internet, web-based platforms, and so on. Okay, so thereafter, once the final operational capability was declared for GPS in 1995, the usage of it definitely increased. Here again, we can note that the development of the Russian technology and the US technology, either in case of the tower-based systems on the ground or the satellite-based navigation systems, were quite parallel. So GLONASS, which is the Russian satellite navigation system, it also declared its initial operational capability in 1993, similar to that of GPS of US, and the final operational capability of GLONASS was declared in 1995, similar to that of the same year as that of the GPS. And then International GPS Service, IGS service, was started in 1994. Now the Cold War era also disappeared and the things became smooth. And that led to the handshake between the US and the Russia, and that resulted into the conceptualization of global navigation satellite system, which is the topic of today's lecture. So what is that system? So primarily GNSS refers to a system which can compute coordinate based on the constellation of satellites belonging to more than one system. So one system means the GPS, another system means the GLONASS, because at that time these two systems were only there. Thereafter, Galileo came from European Union and the BEDO from China. Okay, so these two systems have added later on, but okay. So in 2006, it became possible for the vendors to develop receivers which receive GPS signal as well as GLONASS signal in the same receiver. Before 2006 era, we needed a separate receiver for GPS and a separate receiver for GLONASS. If you want to understand it in a easier way, it is like earlier you might have seen when the single SIM mobiles were there, and suppose you want to carry a SIM card from BSNL as well as the Airtel, then you need two mobiles to carry. But thereafter, two SIM card mobiles came. So in the same mobile, you can put the BSNL and the Airtel, and you can carry the two systems in the form of one mobile only. So same thing happened with the GNSS in 2006. Now this system gets the signal from GPS as well as GLONASS and provides the location of the place. Thereafter, what happened suddenly that the idea was framed that possibly the tower-based systems are not required or they have become redundant. So that thought started a disintegration of those tower-based systems. But soon it was understood that the satellite-based navigation systems are also not totally dependable because of some international developments. So again, the development of the Lorentz system started and the Chayka system started. So E-Lorentz, that is the enhanced Lorentz, also started developing in the early 2000, and the E-Chayka, that is enhanced Chayka, also started. So we are back to the ground-based navigation systems now. So now in 2010, because after the disintegration of Russia, there has been a downfall in the GLONASS and it has not been functioning completely. But with the strengthening of Russia gradually after the disintegration again, the GLONASS also resumes the full-scale operations in 2010. Okay, and then again the GPS and GLONASS both were available. At the same time, the development of quasi-zenith satellite system, which is a regional satellite-based navigation system, started its development by Japanese. Then in 2010, a major development happened and is happening actually, that a new concept has come where we can have receivers which has satellite-based navigation system as well as the E-Lorentz, that is a terrestrial-based navigation system, and E-Chayka, which is also terrestrial-based navigation system. So this system, such systems has also been developed. Then in 2013 to 16 frame, India also developed its own regional navigation satellite system, which is called IIRS or NAVIC, and it is now fully certified and integrated with the latest GNSS receivers. So if you take now the multi-frequency or dual frequency GNSS receivers, you will find the latest receivers, they have the IRSS signals, where the receivers are capable of receiving the L5 and S-band data from IRNSS also. Then in 2019, the BEDO network also completed its operations with some redundant satellites, which also got launched in 2020. So BEDO is also now fully operational. So the technology developed gradually with a 2-kilometer accuracy in Omega, 1 kilometer in inertial systems, and tactical air navigation systems having an accuracy of 400 meter, transit system with an accuracy of 200 meter, Lorentz systems having an accuracy of 180 meter. See, Lorentz systems which had accuracy of 180 meter was a very good accuracy in those days because it was used mainly in the ocean. And in ocean, 180 meter accuracy is a very high accuracy. Okay, so let us not think that Lorentz is giving a poor accuracy. It's giving a very good accuracy. However, for ground services, it can be considered poor. But for ocean services, 180 meter is a very good accuracy. Then the GPS started giving accuracy of the order of 10 to 20 meter, and now with the improved systems, it is giving around 3 to 5 meter accuracy. This LORAN means the long range navigation. Now this is the chip which is there, LORAD D++. This is a 6 centimeter chip which integrates the eLORAN, CHICA and GNSS. So this chip provides the terrestrial based navigation system and the satellite based navigation systems. Both are there, and definitely we can think that in disaster prone areas, in case one of them is not available, the other will assist. So it is a very useful technology. Integrated technology provides us a better solution. Coming to the definition of GPS, which is given by the US DoD, Department of Defense, it provides us the position, velocity, and time. Let us understand it in pieces. So it provides us position, that is the latitude, longitude, and height, and then the velocity with which the receiver is moving, and the time. Because the GPS satellites are using navigation timing requirements with the help of the atomic clocks, they act as timing laboratories also. And most beneficial point when we are using the GNSS or the GPS or the GLONASS is that it has a common reference system for the entire globe. Okay, so how it is useful? So for an example, we can understand here the requirement of the ICAO. This is the International Civil Aviation Organization, which has the responsibility for standardizing the procedures for safe flying of aircrafts across the world. So from their perspective, they have given a definition of the GNSS, which is defined here as follows. It's a worldwide position and time determination system that includes one or more satellite constellation. When one or more satellite constellation, we mean one constellation is from the US Navistar, which is the navigation, satellite timing, and ranging global positioning system, which belongs to US. The second system is the second constellation is the GLONASS by Russia, BEDO by China, Galileo by European Union, IRSS by India, QZSS by Japan. So that is why we have moved from single frequency receivers to dual frequency receivers to now multi-frequency receivers. Okay, and now we are trying to utilize the IRSS or the Navi constellation for our applications as the max, because for it we do not depend upon anybody else. So for the Indian region and 1500 kilometers beyond Indian region, IRSS can be utilized very well, and that is its footprint where it can provide us the coordinates for the benefit of neighboring countries also, especially the SAARC countries. Now these like our vehicles, these satellites also has numbers for identification. There are two types of numbering which are done. One is the simpler one, which is called SV number. That is the satellite vehicle number. So 1 to 11 was reserved for block 1, 13 to 21 was reserved for block 2, block 2A 20 to 40, 41 to 60. So like that, the numbering is done. Or there is another way which is called PRN codes, pseudo-random numbers. So with the help of PRN codes also, the satellite vehicles are numbered. Now, this slide shows the general view of GPS or any satellite-based navigation system. So here it is for the Navistar GPS because it has 6 orbits which are shown here. It can be seen that the system is totally dynamic. Earth is revolving as well as rotating, and the satellites are also moving in the orbit or their respective orbits. So the entire system is dynamic, and similarly the other systems are there. If we look at the general characteristics of the systems for NAVSA GPS, GLONASS, Galileo, BEDO, the positional accuracy is of the order of 10 to 20 meter. Velocity is of the order of again 10 centimeter per second for NAVSA GPS to 20 centimeter per second for BEDO and Galileo. Similarly, timing accuracy is 15 nanosecond for NAVSA GPS, 20 nanosecond for GLONASS and the Galileo and BEDO. BEDO is actually developed in the form of regional navigation system initially, which is called BEDO 1, and then the global system is also developed. So this is one peculiar thing about the BEDO, that the same system has been scaled. See, initially in case of the US and Russia, they have some smaller systems like the Transit and Cyclone. Cyclone was for Russia and Transit was for US. Now these systems has been abandoned and new systems came in like the NAVSA GPS and the GLONASS for global requirements. But in case of Chinese, what they have done, they have scaled up the same system. So they developed BEDO 1 meeting the requirements of the Chinese region and the adjacent region, and then it is scaled into the global system. Now these were the numbers of the first satellites in each of the series. The ellipsoid used for NAVSA GPS is WGS84. For GLONASS, it is parameter is ZAMLI, and for Galileo, it is Galileo Terrestrial Reference Frame. For Chinese system, it is China Geodetic Coordinate System. Okay, so now all the four systems are in different coordinate system, which are very near to each other, but still they are different. But now we are in a good time era, so all the countries and the agencies which are owning these systems are cooperating. So the transformation parameters are known, and thus the satellites belonging to any of these can be utilized for generation of the coordinates. Okay, so although the coordinate systems are different, finally we can work with single coordinate system. So we usually prefer working with the WGS84 datum. Okay, and that means the PZ, GTRF and CGCZ, all these coordinates are transformed to WGS84 and provide us the final value. Then the GPS require minimum 4 satellites signals for calculating the coordinates. We will go into detail of that. Now, as I've told you that this is the system which is the NAVSA GPS, wherein the 6 orbits are used, that is at an average elevation of 20,200 kilometer. The Chinese system is a little complex system where we have satellites in geostationary orbit, in the geosynchronous orbit, as well as the medium Earth orbits. So that way the design of Chinese system is a bit complex as compared to the Galileo, GLONASS and the GPS. Now the Galileo and GLONASS are based on 3 orbit system. So they are having 9 to 10 satellites in each orbit, making the number around 30 in each of them. So these are the kind of designs which has been used. Let me summarize again. So in case of GPS, 6 orbits are used with the minimum 4 satellites in each of them. So that means 6 into 4, that is 24. So minimum 24 satellites are in the GPS system. Since the dependency is high on the GPS system, so a lot of redundancy is kept and around 30 to 32 satellites are maintained. That means each orbit roughly has more than 5 or 6 satellites. So more than 5 at least. So that way the GPS is functioning. Minimum requirement was 4. Whereas in case of GLONASS and Galileo, it's a 3. These are 3 orbit systems and has satellites of the order of like GLONASS is having of the order of 24 to 27, whereas in case of the Galileo, which is yet to complete, it will be about 30. So Galileo is a system under development still. It is partly operational but not fully operational. But our receivers are receiving Galileo signals also, which can be utilized. So that way it is partly useful for us. And the Chinese system is having about 35 satellites or so in its network. Okay, so that means overall we have now currently more than 100 satellites from these four systems orbiting in with their orbits and providing position to us on global basis and in a collaborative manner. And that is what we mean by the global navigation satellite system. Besides these four systems, the regional systems also are used, like the IIRS and the QZSS in the computation. Okay, coming to next step, that how this is functioning. So when the satellite coordinate is known through the ephemeris data, then the pseudo range is computed using the receiver for the GPS or the GNSS signal, and then the travel time, the time t1 at which the signal is started from the satellite, and the time t2, which is the time at which the signal reaches the receiver. So t2 minus t1 gives the travel time for the signal, multiply the velocity of light, that gives the distance, and using that distance we can create a sphere around the satellite position. Now on this sphere somewhere the receiver is there, so there is a lot of uncertainty. But when we combine and intersect two such spheres with the two known positions of the satellites, see, remember Frank McLaurin, what he told, invert the problem. So that means known is in the space, the satellite coordinates are known. What is unknown? Unknown is the coordinate of the receiver, that is the receiver location is the unknown. So once we intersect the two spheres, now the uncertainty has reduced from a sphere to a circle, because now the receiver is somewhere on this circle. When the three spheres intersect, these three spheres, how we have created? With the help of the three satellites and the three pseudo ranges. Pseudo range is the distance between the satellite and the receiver, which is computed by the formula C delta T. Okay, because T1 time is known from the signal, it is embedded in the signal when the signal starts from the satellite, and this information is coming to the receiver. And when it is coming to the receiver, receiver has the quartz clock to compute it. So that gives the T2. So T1 is at the satellite end, T2 is at the clock end, quartz clock in the receiver end. So that way, three satellites can give us the location of the receiver. Now this provides us two solutions here. So one is the real solution, another is the vague solution. So we go with the real solution. With this, there is another problem. Another problem is that the satellites are using the atomic clocks. Satellites are using the atomic clocks, whereas the receiver is using the quartz clock. So these are two different quality of clocks. The atomic clocks are highly accurate, whereas the receiver clocks are less accurate and less precise. So that gives rise to a synchronization problem between the timing, that is T1 and T2, and that is called the clock bias, which also need to be resolved. So now what happened? We have had already three unknowns. What were they? X, Y, and Z. X is the longitude, Y is the latitude, and Z is the height. Now there is a fourth unknown, that is the clock bias. So X, Y, Z, and B. So now four unknowns are there. So we need four equations to be built, which are independent of each other, and thus we require four satellite signals minimum to resolve the position. So that's what's shown here. T1 is the transmission time, T2 is the reception time. That is, so this gives the delta T, and this is the velocity of light. Okay, and since this technology developed as part of the Cold War era, the signals are designed from the basic definition itself as one-way ranging. That means the device will only receive the signal; it will not send back any signal. Okay, so receiver only receives the signal; it do not send back. So that means if you have a GPS, nobody can track you because receiver do not send back your information to anybody. If you are being tracked, then or if you want to devise a system like the cabs are using, that means there should be a GPS along with the tracking device. So the tracking device will send the coordinates back to the headquarter, wherever the cab headquarter is there. So they will always know where is the particular cab, like Ola service or Uber. They utilize such services and tracking devices. So I think, shall I stop here and maybe I can take some questions from the uh, viewers or the participants if they wish. Okay, so I think I will move ahead. So now thereafter, we have the GPS signal structure, how the GPS signal has been designed. One minute, okay. So basically GPS has two carrier waves. I'm talking about the basic GPS design. The GPS which we are having today, or the GNSS which we are having today, is a highly developed system which has many things which has developed and added over time. So first we will discuss the basic design. So basic design included two carrier waves, that is the L1 carrier wave and the L2 carrier wave. L1 carrier was having the coarse acquisition or the clear access code, which is used for civilian services nowadays through the SPS standard positioning method. Your mobile, your handheld GPS devices, your car GPS chip, all are based on the CA code, whereas the defense system, they are using the precise code, that is the Y code. So certainly the GLONASS precise code is accessible to the GLONASS receivers or their defense agencies only, whereas the US signals, they are accessible to the US agencies only. Okay. Besides this, L1 and L2 and CA and P codes, here P code is an encrypted code because it need an authorized receiver. So it is an encrypted code, and after encryption it becomes a Y. Besides these two codes, there is a 50 bit per second signal also, which provides the almanac and the ephemeris. What is almanac? Almanac is the chart of all the satellites in the constellation. Like in GPS constellation, all the 30 satellites information will be downloaded in the receiver, whereas the ephemeris is the instantaneous coordinate of the satellite in the region. Because at a time you may be receiving the signal from 4 satellites, 8 satellites belonging to one constellation. So those coordinates will also come to the receiver in the form of ephemeris data. So ephemeris provides you instantaneous coordinates, whereas the almanac provides the entire constellation information. Now with the development of time, new systems also came, and then the L5 carrier wave has been added now for indoor applications and anti-jamming features and search and rescue operations, safety of life operations. So this L5 signal with I5 code and Q5 code has been added, whereas the L1C code and L2C are also added. along with AM code for the military. So that's why I was telling. So this is the current scenario of the GPS signal structure. So the initial structure was like this. Just to repeat, this was the initial design. You can say the zero level design, and with the development, the latest or the current design is this one. Okay, so standard positioning services are being utilized for the civilian operations requirements, whereas the P code or the AM code based services are used for the US defense or their friendly countries. So like that. Whereas safety of life, the entire system provides help for that. However, L5 is especially designed for indoor applications, anti-jamming features, and safety of life based applications. Besides L1 and L2, there are L3 and L4 frequencies also, which are available to US agencies only to identify if there is any nuclear detonation anywhere on the globe. So this is accessible to them only. The L1C and L2C are still in pre-operational testing mode, and soon we will be able to use them also fully. So this is the scenario when we combine all the systems, global navigation system, that is the GPS, GLONASS, Galileo, and VIDO all together. So the main features of them are that the inclination of GPS satellite orbits are 55 degree to the equator. For GLONASS, it is 64.8 degree. For Galileo, it is 56 degree, and for VIDO, it is 55 degree. However, VIDO use multiple type of constellations, as I have told you: medium Earth orbit, inclined geostationary orbit, and the geosynchronous orbit. So that way the VIDO systems are a bit complex. Their revolution times are nearly 12 hours for the GPS and GLONASS. That means these satellites complete about 2 orbits per day, whereas Galileo has 14 hours revolution time and VIDO has 12 hours 53 minutes for the medium Earth orbits. Then they provide different type of services like the standard positioning service and the precise positioning service. And similarly, other services are there with the receivers. I will emphasize on maybe one system more because time is limited, and all the systems have parallel facilities with them. Now, in the GPS, like we define the first generation computer, second generation computer, third generation computer, or the fighter planes in the form of different generation. The GPS also has various generation of GPS satellites, which we refer as blocks. We do not refer them as generation, but they are actually generation. So whenever there is a technological change in the GPS satellites, we name it separately. So we have block 1 satellites which have completed their life. They were launched between 1978 to 1985. Then block 2 and block 2A came, under which 27 satellites were launched between 1989 to 1997. And thereafter, block 2R and 2RM also came, where about 20 satellites were launched. Then the block 2F, which is the major system in which we depend. So currently our services most of our services depend upon block 2F, and the latest system which is now under development is the block 3. So block 3 is the latest system which has been built around the concept of cyber security and defense requirements. It has required a total change of hardware and software. So it is costing the US of the order of $6 billion because of these requirements of the changing times. And out of these $6 billion, $500 million are just for the software OCX itself, which takes care of the cyber security, anti-hacking, and all those things. The M code is used is a powerful GPS-3 signal for the military users, which is used by the military aircrafts and are more secure systems for jamming or spoofing. So these Block 3 services have started now, but since the number of satellites in Block 3 are less, gradually this will grow. Okay. So what we can understand here, currently our main dependency, which is going to be there for quite some time, maybe for one more decade, we will be more dependent on Block 2F, during which time the Block 3 will also be developed, which is also divided into Block 3A and 3F. Okay, so the new numbering comes with the development in the technology, either in the hardware, software, in terms of weight, efficiency, electronics. So because over time these satellites have become lighter and more efficient. Okay. So why do GPS satellites have more eccentricity? That was the question. So see, all the satellites, like the electrons, lose their energy and come down to the lower orbit, and as they get more energy, they jump to the higher orbit. Similar tendencies are there in our based on the physics models, the relationship between the solar system, Earth, and the satellites. So the satellites also have tendency to move a bit away from their orbit, and for this the maneuvering of satellites is also required. Okay, so that is one major task of the ground control centers, to attend to these requirements on 24 hours 365 days, and to see that the satellites are in their orbits. If they are not, if they are moving out, then they need to be maneuvered. Coming to the next point, that now the satellites are there, and we understand that they are part of a very dynamic system, and at every moment there are different satellites which are visible from one place, and the number also changes. Sometimes 7 are visible, sometimes 8 are visible if you are using a single service system, either a GPS or the GLONASS. But if you are using a multi-frequency receiver, because we have now a GPS, GLONASS, BIDO, Galileo, IRSS, QZSS, these 6 systems are there roughly for our region. If I take example of Dehradun, at our location we are very easily getting about 40 satellites at any moment in our GNSS receiver. 40. Okay, so that is the kind of number of satellites which we receive now, and which is very good to provide us a very high accuracy. Now, earlier when we used to have less satellites, so let us assume that we are receiving the satellites signals from 4 satellites only, like this, and the 4 satellites are placed like this, and this center is the location where we have the receiver on the ground. So one satellite we have overhead, and the 3 satellites are like this. So that provides a very good geometrical solution. The geometrical explanation is like this, that when we create the spheres which we need to intersect to do the trilateration and finally locate the position of the receiver, the uncertainty is less. So this provides us a good dilution of precision. It is like a root mean square error, what we use in our day-to-day statistics. So however, this DOP is a unitless number, and if the DOP is low, then we have higher accuracy. Now, even if we have more number of satellites, but they are skewed like this, then what happens when we intersect various spheres, it provides larger uncertainty. Larger uncertainty means less accuracy. So in nutshell, what happens that if you consider these fingertips as satellites and bottom of my palm as receiver, the thumb rule is higher the volume, more is the accuracy. Lower the volume, lower is the accuracy. Okay. So this diagram, which is shown here, it provides a good GDOC scenario where we have less uncertainty and high accuracy. Whereas if we have this kind of scenario where we have a skewed setup of satellites, then we have high uncertainty and low accuracy. Now, if we are talking about the accuracy of latitude, longitude, height, and time together, then we refer to it as geometrical dilution of precision. If we are interested in latitude, longitude, and height, then we refer to it as positional dilution of precision. If our interest is in the planimetry, that is the x and y only, that is the latitude, longitude, then we use horizontal dilution of precision. Whereas if our interest is in the height, then we refer to as vertical dilution of precision. So if the DOP value is between 1 and 3, it's called very good. If it is between 4 and 5, it is good. And fairly good up to 6. If the DOP value is more than 6, then we consider it to be less reliable. So we prefer not to do survey at that time. Now the GPS coordinates or the GNSS coordinates are with respect to the ECEF coordinate system, which is the Earth-centric, Earth-fixed coordinate system. So the GPS has XP, YP, ZP coordinates with respect to the center of the Earth, and the point has XA, YA, ZA coordinates. So this equation AP equal to root of XP minus X square plus YP minus Y square plus ZP minus ZA square root. So that provides the pseudo range, that is the distance between the satellite and the receiver. Now why it is called pseudo range? Because there are certain errors in the computations. So pseudo means false, range means distance. So instead of calling it a range or the distance, which is the surveying terminology where we refer the distance as the range. So since there are errors in the range, we refer to it as the pseudo range. So by now, I think we are very clear that we are computing the coordinates, that is the x, y, z, that is longitude, latitude, and height of the receiver at any point, wherever we are doing the survey. Point number 2, when we are getting the GPS receiver, we can have either the, from remote sensing perspective, we may be using it for the ground control points, or maybe for checking the accuracy of digital elevation models or some other products. Now there are different kind of receivers in the market, and we have to procure them for our requirements. So the single frequency receivers, which are mainly based on the L1 frequency and the CA code, they are capable of providing us an accuracy of 10 to 20 meters in a standalone mode. But when we are using the DGPS system, differential GPS system, then these single frequency receivers can provide us an accuracy of 1 centimeter plus 2 ppm. Similarly, the dual frequency receivers, which can receive L1 and L2 signal both, can provide us an accuracy of the order of 5 millimeter plus 1 ppm. Okay. So 1 centimeter plus 2 ppm is the accuracy of single frequency receivers, and dual frequency receivers have 5 millimeter plus 1 ppm. So that was the accuracy which we have been receiving for last around 2 decades, we can say, when we use the DGPS. But the technology has again developed over time, and with the latest receivers which are there in the market, if you see their brochures and utilize them and process the data, then currently what we are getting from the latest receivers, the accuracy is from single frequencies of the order of 5 millimeter plus 1 ppm, and from the dual frequency or multi-frequency receiver, we are getting horizontal accuracy of the order of 3 millimeter plus 1 ppm or 0.4 ppm, and vertical accuracy of the order of 3.5 mm plus 0.4 ppm. So if we see this, that now there is a marginal gap only between the single frequency and dual frequency, because single frequency DGPS receivers you can get at a cost of about less than 5 lakh rupees, which includes a base and a rover. Base station is a station which is placed at a known location, whereas rover is a GPS system which you take in the field from point to point to compute new coordinates. So base is established at a known location from previous survey, and rover is taken from to the field. So this system cost about 4 lakh to 5 lakh rupees, whereas this system costs you around 16 to 20 lakh rupees or more. So 4 times difference is there almost. So for this 2 mm, why should we spend that much money? Okay, but what happens that we have to understand the different working environment. The limitation with single frequency receiver is that the baselines can be of the order of 15 kilometers only. So that means if you are working with the study area which is smaller and has baselines of the order of 15 kilometers, then you can go ahead with the single frequency receivers. But if you have a larger study area or continental area or a countrywide area where baselines are of the order of hundreds of kilometers to thousands of kilometers also, then you have to work with the multi-frequency receivers only. So for photogrammetric control, we are using these receivers, and for the real-time computation. And because, yeah, I will attend to these questions also, how GPS works in a tunnel, and so I will come to these questions. Okay, so let us stop here at this slide, and I will try to reply to your questions. So one question was that how these GPS signals can be used in tunnel. So in tunnel, we will not be getting the GPS signal. Okay, that is one issue is there. But there are system solutions which are given. There is a jet blade technology which is developed by the Trimble. So you will have a GPS receiver outside tunnel, and you may have a reflector or something, device inside the tunnel. So that way indirectly you will be able to compute that. So directly, if you want to get the coordinate in the tunnel or in an underground mine, that will not be possible directly through the direct methods. But indirectly, you can get through techniques like coordinate conversion and all. Similarly, Leica is providing a smart station. So in a smart station, you have a total station along with a GPS receiver. So there also you have a reflector, 360-degree reflector is there. So using 360-degree reflector in such difficult areas, you can again calculate the coordinates inside the tunnel or in other difficult situations also. But in general, if you say you have a normal arrangement of GPS, single frequency receiver, dual frequency receiver, and directly you take it into tunnel, it will not be possible to get the coordinate. But there are other technologies which are coming up, and you can get the coordinates from them. Any other question was there? I think one more question was there. Okay, so we'll move ahead, and then we will again come back to questions. So now there are 3 classes of GPS receivers which we have developed, because we have GPS receivers currently from 5,000 rupees to 10 or 20 lakh rupees. So there's a large variation in the GPS receiver devices. So these devices are in general classified into 3 types. In the geodetic class receivers, which basically we use for precise applications, we can get accuracies of the order of sub-centimeter level. That is, we can get accuracy of the order of millimeters by applying the specific surveying techniques and processing techniques. These are used for highly precise mapping, surveying requirements, and geodetic applications. They are little bulky and quite expensive also. This choking antenna, which is used for arresting the multipath effect, itself weighs about 3 to 5 kg. So you can understand these systems are quite bulky. Then mapping rate receivers, which may be handled or maybe on tripod. These are providing us an accuracy of the order of 3 meters or so. These are portable relatively and less expensive as compared to geodetic class of receivers, and are good for the automated mapping or facility management mapping requirements, and their integration with the GIS, such as the power GIS, where you may have requirement of mapping all the public utilities like the electric poles, transformers, mapping the sitting places in the parks. So for such things, this kind of receivers can be utilized. For specific applications, mapping of trees, these kind of receivers can be utilized. Then there is a navigation requirements are there. So these provide you the accuracy of the order of 10 meters, such as the chips which are embedded in our cars nowadays, and they are assisting us by voice. Okay, so with the origin destination problem which you have given to the software in your car, it may take you that you take left turn, you take right turn. So don't go by those commands, okay, because you may be still 10 meters away from that point. So we have to use our navigation skills also along with the commands which we are getting from these. There are different sources of errors like selective availability, which was a intentional error incorporated into the signals by the US agencies so that the users do not get best quality signals. So that was the case till 1st May 2000. Thereafter, this selective availability, which is referred as SA, this has been disabled. So currently we are getting the good signal only. Then there are certain clock errors are there, ephemeris errors, which are the errors in the position of the satellite. Then atmospheric delays are there, multipath errors are there when we receive the signal which hits the building or neighboring place and then comes to the receiver. So that is called multipath effect. These errors contribute to the total error. Then there are certain system errors like the receiver errors. So what happens that when we are using the standard GPS, that is the single end GPS, either in the form of GPS or the GPS in your watch or in your mobile, so that is providing you an accuracy of the order of 10 to 20 meter. In the era when the selective availability was on, it was providing an accuracy of the meter of 70 to 100 meter. Once the SA feature was disabled, then only we started getting this 10 to 20 meter accuracy. Okay, now the importance of DGPS. So now for engineering surveys or the construction of bridges, road alignment, canal alignment, whatever measurements we are doing in the field, or for georeferencing of the satellite data sets, we need the control points from DGPS, because DGPS eliminates the satellite clock errors, eliminates the orbital errors, and reduces the ionospheric and tropospheric errors to a greater extent. However, receiver noise and the multipath remains. Okay, so that is why we are using the DGPS now, and that provides us an accuracy of the order of few meters if we are finding the solution from CA code. Whereas if we are using the phase solution, there are two types of solutions which we get for the DGPS. One is the phase solution, another is the code solution. So code solution gives us accuracy of the order of few meters in case of DGPS, whereas if we are using the phase solution, we get the accuracy of the order of millimeters or centimeters. So that is the way these differ. So any questions are there? I think you can ask. So now, like the sunrise and like the sunset, satellite also rises above the horizon and starts providing signal to the receiver. So at that time, the signals which are from the lower elevation places, they provide larger errors, and that is why in the systems we do a setting for the elevation angle. So that means if we provide a mask angle or the elevation angle as mask angle of 15 degree, then the solution will not utilize the signals which are coming from the satellites which are sending signals within this zone. Okay, this shaded zone. So these signals will be kept out of the solution. So that is why we use the mask angle. So that is what I was telling earlier. The selective availability was operational and was providing us an accuracy of the order of 30 meter. But once it has been switched off, we started getting an accuracy of 10 to 20 to 10 to 30 meters. You will get different references in different places, but currently what we are getting is a better value as per the last report released by US DoD. The latest receiver systems which are developed recently in last 2 years or so, where they are capable of providing 3 to 5 meter accuracy in a standalone mode. Okay, but if we are using the little older systems, then again our accuracy will be of the order of 10 to 20 to 10 to 30 meters in standalone mode, whereas in the DGPS mode we can definitely get the accuracy of the order of centimeters or millimeters. Okay, so this shows this slide shows a situation where we have smaller baselines less than 10 kilometers, where possibly the atmospheric conditions are same for these two receivers. But if we have longer baselines, then the conditions may be different for two places where receivers has been kept. At one place it may be sunny, other place it may be raining, or there may be snowfall. So atmospheric errors will be different. So we may need certain softwares like the Gamut or Skipro, which are scientific softwares for resolving such baselines for higher accuracy. If they are in similar conditions like this, we can possibly resolve our position with the softwares which we are getting from our commercial vendors. So I think now maybe we can take up more questions relevant to your areas, because I can go and go on for different things like tropospheric reflection, atmospheric reflection, which are also providing us larger errors, and these errors can be dependent on the season and time when we are doing the operation, but these can be reduced with the use of DGPS. So possibly you can ask certain questions now. We have to avoid the use of GPS installation near the electric poles, because ultimately we are dealing with the electromagnetic radiations which can be affected by these electromagnetic services, like from the electric wires and electricity. So these we have to avoid. So you can ask certain questions. Then human error should also be avoided. Whenever we are surveying, we should keep record of everything properly in terms of units, in terms of measurement, in terms of settings, all that we have to take care. Okay, so as I was telling, in standalone mode, you can get accuracy of the order of 10 to 20 meters. And this is the latest report which I was referring to. It is the 5th edition report released on April 2020, that the latest receiver will have a capability of providing horizontal accuracy of the order of 3 meters, whereas the vertical accuracy can be provided of the order of 5 meters for 95% of the time. Okay. So this is the link for the report, which is given at the bottom of the slide. So the DGPS solution is providing the higher accuracy, as we have discussed. So this is the scenario where we are using the DGPS service. One station kept at a known location and another is used as a rover at other location. So I will stop here and now we will take up the questions. Okay, I missed the query DOP. It is from Ajit Kumar. DOP is a dilution of precision. It is a parameter designed for GPS, similar to statistical parameters like RMSE, what we use for statistics. So DOP helps us or guides us in the assessment of the quality of signal. If the quality of the signal is good, very good, if it is between 1 and 3, the table which I have shown you earlier, and it is DOP is utilizable by anybody. Expertise is not needed because it is displayed on the GPS receiver. Anybody from any field can understand that, and it is a unitless number also. So I think 3 questions only we received, and these I have answered. Any more questions are there? Kindly please ask. So since as long as I do not get question, I will keep talking to you, and as soon as I see a question, I will reply to that. Okay. So now what I understand that the course is for disaster management. So basically, what GPS can contribute to that? That is of importance. Okay, so first point is that for any of our work, for the mitigation exercise or for the preparation for our future disasters, we are making the databases. So let us understand that those databases has to be accurate, as accurate as possible, and GPS basically plays a role there. It provides you good coordinates. It provides you good photogrammetric solutions for triangulation. It helps us in development of good digital elevation models. Okay, so that is one way to look at it. Another way is if we see today's scenario, then if you might have heard that two private companies, I think they have been called up during the recent Chamoli disaster. Uh, and what they have done, they have come with the UAVs, where they have flown the UAVs. So UAVs can also see in the areas where we are not able to physically go. So UAVs can inform you through their optical data set that where are the casualties or the possible people in distress who need help. So those UAVs will have the GPS embedded with them along with the geotagged photographs and videos. Okay, so there also GPS is helping you, but that is like post-disaster. So pre-disaster is like database preparation, which can be prepared well with the help of utilization of GNSS. Post-disaster scenario, we can use it to get the coordinates of the people in distress with the help of the UAVs and similar such services like SOS, like IIRS receivers are there, which are given to the fishermen. Now, those fishermen, when they are near to the international border, they get a signal from the receiver itself, then that be aware that you are moving towards the international borders, because if they go across the border, then they may be captured by the other country forces. So these kind of applications can be there for the GPS. Actually, n number of applications are possible. Okay, so swarm GPS is another swarm UAVs. is another technology which is developing in the defense world currently, but actually is of high usage for disaster management also, where you can move a set of GPS together to obtain the information in the affected areas to save more life in the flood affected areas, in the earthquake affected areas, in the maybe nowadays so many fires, forest fires are happening. So in the such cases also, so the GPS can assist you. So we have to understand here again that it is an important means to give us the coordinates. It do not provide direct solution. Okay, for hand holding we have to go there. If you have to save a person in a flooded water, you may have to send a helicopter to rescue that person. But where you have to go, how you have to go, that in that process, the remote sensing and the GPS can assist the disaster management personnel. So I think I will stop here now, and I will take up any queries which are coming on the way.